So we are starting. I remind you where we are finished yesterday actually. Right. So we developed by Legendre transformation, additional thermodynamical potentials, right? So we had energy and we had free energy. So there is E, it's energy, F, which is equals to E minus Ts, it's free energy. Okay. What else did we had? Enthalpy, right? So what was enthalpy? How we defined it?
E minus F minus plus PV.
F plus PV.
So E plus PV.
E plus PV. So it is E minus P multiplied by V. We had Gibbs potential, right? What was the Gibbs potential?
The F minus PV.
Okay, so Gibbs was E minus Ts minus PV. So this is enthalpy. This is Gibbs potential, and we also had grand potential, which is E minus Ts minus mu n. So this is grand canonical potential.
Can I ask a question?
Sure.
When they send the quizzes, I saw that the quiz is...
We can discuss the quiz at the end of the lecture. Fine?
Okay.
All right. Now, the idea with all of those transformations is that we had energy which was a function of entropy, it was a function of volume, it was the function of length, it was the function of the number of particles. Okay? So each of those variables have a conjugated variable that's associated with it. Right? So S is associated with what? With temperature, which is dE to ds. Okay? Volume is associated with, in our case, it's minus pressure, okay, which is dE to dV. Length is associated with tension, which is dE to dL, and number of particles is associated with chemical potential, which is dE to dN. Now, those are extensive variables. Those guys, which are generalized forces, they are intensive variables. Intensive variables. Now, the transformation or Legendre transformation, what it generally does is transform a general functional, which is a function energy, which is a function of only extensive variables. It can transform it into another function, can be free energy, enthalpy, Gibbs potential, grand canonical, or whatever other function that you like, by using a transformation. All right, so I don't like some specific variable. I can replace it with the conjugated variable, which is going to be an intensive variable, a generalized force. And by doing what? So if I have, let's assume that I had E, S, V, L, N, and I had some additional variable Y. Okay, so I could say that let's invent a function A, which is E minus dE to dy multiplied by y. Okay, and if I call dE to dy x, A is going to be a function of S V, L, N, and X. And dA to dx is going to be equal to -1. Okay? So this is the general procedure. You can replace extensive variables by intensive variables, but not just any intensive variables, only variables that are associated, conjugated to your original extensive variables. Okay? So this gives plenty of room for a lot of games for exchanging variables and choosing the right variables for your problem. You will see that for some problems, the energy is the best way to go. For a lot of problems, it's actually the free energy. For some more complicated problems, it's going to be grand canonical potential. Okay? It's all going to depend what kind of problem do we have in our hands. All right, so now why we did all of this? Remember, the goal is still to define what happens at equilibrium. Okay? So we know already what happens at equilibrium. At equilibrium, the entropy is maximal, the energy is at minimal, and I told you that also all of those, and you can show it exactly as I showed it for the energy, all of those transformations of the energy are also going to be at minimum with respect to at minimum at equilibrium. Okay. So for energy, what you keep constant entropy, and then with respect to the other variables, the energy is going to be at minimum. But when you make a transformation from the energy to entropy, to free energy, the entropy is no longer a variable that describes your free energy. So what we are going to keep constant?
Temperature.
The temperature. We are going to keep constant the new variable, the conjugated variable that is associated with the free energy. So the free energy is going to be at minimum with respect to everything else when the temperature is kept constant. Right? So this is already an advancement, right? So because in a lot of cases we cannot say, well, I'm keeping my system at constant entropy. It's hard to manage that, but I can keep my system at constant temperature. So therefore, the idea, if I do know what's the temperature of the system, and I'm keeping this temperature constant as a function of time, it's not going to be going up, it won't go up, won't go down, I know that my free energy is going to be at minimum. Okay, so the same happens for enthalpy, for Gibbs, and for grand canonical stuff. Now,
The temperature can change in the function of place.
the temperature?
Yeah.
No. Okay, great question. We'll answer it in a second. Okay, in a second. Okay. So the next question that I would like to raise is what happens to generalized forces which are intensive variables at equilibrium. Okay. So let me rephrase this. I'm asking the following thing. Let's assume that I have two systems. System A and system B. And those two systems are in contact with each other, and they are separated from the outside world. So there are some adiabatic boundary conditions, no heat is entering the system, nothing really happens. Okay. So this is system A, and this is system B. Now they are in contact, and they are in equilibrium. So I'm looking on the intensive variables, my generalized forces. What are my intensive variables? I can look on T, I can look on P, I can look on mu. The same happens with tau. So I have TA, I have PA, and I have mu A. Okay? And I also have TB, and I have PB, and I have mu B. Okay? So, and this is related to your question. Can the temperature be different as a function of position? I can say, well, I had one system, I just drew a line over here, right? So this is position small coordinates, those are far coordinates. They are interaction with each other. The whole system is in equilibrium. And I ask, what happens to those generalized forces, but actually intensive variables? Okay. Now, it's crucial to say that everything is an equilibrium. Okay. So what do you think will happen? We actually already seen something like this for the temperature. Okay. What do you think will happen? Intuition, physical intuition. They'll be equal. Why?
We showed for temperature.
We show for temperature, and therefore we should hold for everything else. Okay. I told you what happens at equilibrium, right? So what happens at equilibrium? Yes?
There is no current of heat.
No current of anything. No current of anything. There is no current of anything. There is no current of energy. There is no current of volume. There is no current of particles. There is no currents on any scale. Now, what create currents? Forces, right? So I will have a current in this direction if I have some differences between the forces or pressures or whatever, and I have some average force that's pushing me to the side, right? Otherwise I will have just some random fluctuations. It's only forces that are keeping me driving in a specific direction. So no currents, no differences at different forces. No differences at different forces, although intensive variables are my generalized forces. Okay, so this is the idea why I expect that TA is going to be equal to TB, the pressures are going to be equal, and the chemical potentials also have to be equal, right? But let's show it. Okay, so the idea is that the basic definition of equilibrium, no currents. No currents, all the forces have to be equal. Okay, so how do we show it? I already showed you this trick. We use the property that the energy is at its minimum. So the difference of, let's say this is UA plus, or like this, DEA plus DEB is going to be equal to 0. Right? Because the system, it's in equilibrium. Now, what is DEA? What is DEA? Is dA dSA minus PA dVA plus mu A dNA. Okay. Plus TB dSB minus PB dVB plus mu B dNB. A lot of intensive variables and a lot of extensive variables, and we have two different systems, so quite a mess, but there are connections between all the extensive variables. There is the total energy, the total system has no correlation to the outside world, so the differential of the energy is going to be 0, and it's at its minimum. Okay, at minimum.
But this is the differential of EA or EA plus
I'm sorry. So this is DEA. Let's write it like this, and this is DEB. Better? Okay. Great. Now we also know the following thing: VA plus VB equals to the total volume of the system. SA plus SB equals to total entropy of the system. What else we have? NA plus NB equals to the total number of particles in the system. Therefore, D of the left-hand side equals to the D of the right-hand side. but the system is not in contact with the outside world. So the total volume, what's going to happen to it? The differential, this is 0, this is 0, this is also 0, right? So we obtain the following relations between the differentials of the extensive variables. It basically says that dVA equals to minus dVB, and dSA equals to minus dSB, and dNA equals to minus dNB. Okay. So let's introduce everything inside. So we have dEA plus dEB equals 0. Now instead of SB, I'm writing minus DSA. Instead of dVB, I'm writing minus dVB. Instead of dNB, I'm writing minus dNA. So what we have dA minus dB DSB plus, sorry, DSA, yeah, thanks, plus minus PA minus PB dVA plus mu A minus mu B dNA. So all of this equals to 0. dE equals, yeah, so the total entropy is, we are in equilibrium, so the entropy is not going to change. Right. Okay, so what are those DSA, DVA, and DNA? Those are small transformations, fluctuations of the volume from one system to another. Okay, one system can grow a little bit, the other system will shrink a little bit. The pressure, the entropy here will reduce, here it will grow. The number of particles, here it's going to grow, here it will be reduced a little bit. Okay? Those SA and DNA and DVA are free variables. They can be positive, they can be negative, they can be whatever you like. Okay? But this condition still holds. So it doesn't matter what's the value of DSA, what is the value of DVA, what is the value of DNA, the condition holds. Right? So when it happens, there is only one situation when no matter what DSA is, what DVA is, and DNA is, that this condition is happening. It's when this guy is 0, this is 0, this is 0, and this is 0. Because DSA, DVA, and DNA are completely independent. Therefore, we arrive.
Stas,
Yes.
how could the A quantities change if the system is in equilibrium?
What is equilibrium?
No currents.
No currents. Fluctuations allowed? Yes? Yes. So there could be, so when I'm saying, you remember what I said about equilibrium. Equilibrium, it's the average behavior. Okay? On average, there is no flow from here to there. But from time to time, okay, so if I'm looking at this marker, the number of particles on this marker, although it is an equilibrium, is constantly changing. Some molecules leave the surface, and some molecules are going backwards. On total, there is no net change. But from time to time, there is a little bit less particles on this marker, and from time to time, there is a little bit more particles on the marker. Fluctuations are allowed. Okay? So those guys, you can take them as small fluctuations. Right? So what we got? We got TA equals to TB, PA equals to PB, mu A equals to mu B, and in general, equivalence of intensive variables between different systems in equilibrium. So if we have two different systems in contact, okay, all the intensive variables of those, and those two systems are in equilibrium with each other, all those intensive variables, all the intensive variables of those two systems are going to be exactly the same. Now, thermodynamics is a macroscopic theory. It assumes that there are no microscopic parts, right? So basically we can say the following. If this is our system, okay, and this is x-axis, and this is y-axis, okay, and we are going to separate the system to many other systems. This is going to be system A, this is going to be system B, this is going to be system C, system D, and system Z. Okay. This condition says it doesn't matter how you separate exactly the subsystems, right? If the whole system is in equilibrium, right, there are no currents from A to C and CD and BD, and this means that for this system, all the intensive variables are going to be equal to each other. Right? So they're in equilibrium. There should be no differences between the temperatures, no differences in pressures, no differences in chemical potentials. So, in some sense, equilibrium is boring. It describes something which is some kind of bed. So if you look on every living system around you, it's out of equilibrium because there's constant current that occurs around us. For systems in equilibrium, everything is dead, nothing is flowing from one place to another. There are some small fluctuations, okay? On average, nothing happens. All right. Yes?
If I take the system that you drew back, just two boxes, and I push a little bit.
Push yes.
And then give it to go to equilibrium again.
Okay.
How they get to equilibrium again?
Great question. Okay. So what I described over here is what happens at equilibrium, right? So basically, I used one specific condition. A specific condition that at equilibrium, the energy is maximal, so the differential has to be 0. Now, what you're asking is, well, you're not just saying that it's some critical point. It can be minimum, it can be maximal. So the first derivative, or the differential is 0, it doesn't tells me that if this point of equilibrium is indeed minimum point or maximum point. Maybe, so that's what I'm referring. Is when you look on a function, any function in general, okay? So let's assume that it has minimal. So at this point, the function of x, this is minimal for x0, and this is x1. The derivatives at this point, the derivative is 0, and also the derivative at this point is also 0. But the behavior of a particle, so if you're assuming that this is the energy, okay, and you're going back to mechanics 101, if you take your system and then you pick a ball, so let's assume that this is a potential energy. You put your ball exactly at this point, it's going to be stable. Right? So equilibrium, in some sense, is telling us something about the stability of the system. Meaning, I am putting my system exactly at this point, it's not going to move. The same happens over here. I'm putting my system exactly at this point, small ball, okay? It's not going to move, right? Because, if you remember, forces are related to the derivative of my potential energy. So the derivative here is 0. Nothing is pushing the system not to the left and not to the right. The same happens over here. But, and this is related to what you asked, if I take my small ball and I push it a little bit to the side, to the right. So what will happen if you're around minimum? The external forces will drive me backwards towards the equilibrium, right? But if I'll do the same trick, if I'm sitting on top of around a maximum, if I push my system a little bit to the left or a little bit to the right, the external forces will drive me away from the equilibrium. Okay? So what we have used so far is we looked only at minimum position. We haven't tried to see what happens if I push a little bit to the left or push a little bit to the right, as you said. Right? This condition was sufficient in order to tell us what happens to all the intensive parameters. Okay? They're equal to each other. We haven't used that it's a minima or a maxima of the energy. The only thing that we used, that the derivative was 0. Your question is, okay, so what happens around? It has to be minimum, as you told us. So it's not enough to tell what happens to those intensive parameters at equilibrium. We also have to define what happens to their derivatives. Okay? So this is the next task. We know that they are all equal, but how they change. So in equilibrium, there should be something about the derivatives of the extensive parameters or the intensive parameters. Okay? We'll deal with this in a second. Yes?
All those parameters are quantities of the system, but what happens if I have a generalized force, which is intrinsic quantity of the particles, let's say charge or magnetic force?
Great! So we do the following thing. So we have here TdS, and we have minus PdV, and we have plus mu dN, right? And then we will have your particles. How we will call them? Zeta d psi.
Okay.
What is psi? Your extensive quantity that describes the whole system. What is the zeta? Is how they affect the energy. Okay, zeta is going to be dE. This is d. dE to d psi. And what I'm going to answer you is that this zeta across the whole system has to be equal. Okay. Give me exactly the extensive variables that you're referring to. I will see how it affects my total energy. I will look on its derivative. This derivative, the derivative of the energy with respect to your new variable. This derivative is going to be my generalized force. And this generalized force is going to be the same for system A, C, B, D, and C. Okay?
I still can't understand how could it happen. Let's say psi is
Magic of
voltage.
physics.
No,
Yes.
let's say psi is voltage.
Okay.
So zeta should be charge.
Yes.
So
if I have differences in voltages, I will have a current, and this current will continue till there are no differences in voltages, and then I will reach an equilibrium.
But each particle still will have different charge. Let's say I have two types of particles.
Mm-hmm.
Okay, so each particle still have.
Eventually, the system will reorganize such that there are no currents. Okay? So the thing that will happen, so you can state that you can start with non-equilibrium steady state, but eventually after a while everything will start to move, okay? And after it's moving a little bit, it will reach this equilibrium state. I'm not telling you how exactly it's going to move. I'm not telling you how much time it's going to move. I'm just saying that eventually after a while, and this while can take millions of years, it will reach equilibrium steady state. That's our experience. Okay?
In equilibrium, it means that in charge,
Dead.
it means that let's say charge density is uniform.
Yes, unless you have some additional constraints.
Okay.
Okay? So you can introduce other constraints. You prevent particles from moving, so it's going to be a little bit different equilibrium, and you have to describe this a little bit differently. Okay? Other questions? Yes.
So we can safely assume that every physical system will reach equilibrium given a certain amount of time?
Okay, so this is a tough question. So in general, this was our experience until glassy systems were discovered. Okay, so basically for almost any physical system there is a time scale. The time scale that defines how much time it's going to take the system to reach equilibrium. But there are glassy systems, and glassy systems, at least on the, how much time you're already measuring stuff, decades, maybe 100 years, So there are systems that even on this time scale, they haven't reached equilibrium. That means, well, two things. Either we haven't measured enough, so maybe in another 200 years they are going to reach equilibrium, or they have no time scale, therefore they will never reach equilibrium. For practical reasons, because you cannot measure for 200 years. It's impractical. We treat those systems as out of equilibrium, and those are specific glassy materials. There is a question about glasses. Different types of glasses, okay, not all the glasses, they are out of equilibrium systems. Okay? Other questions?
Harmonic oscillator is in equilibrium.
Well, if you define a temperature for the harmonic oscillator and you will eventually keep it out of touch of every other students in the room, that it will reach equilibrium. Where it will go, your harmonic oscillator. So if this is your potential, right? This is your potential. This is your harmonic U of x. This is x. Okay? And eventually it will reach this point. Very simple and very stupid and very boring. Okay? Okay, so where we are going, so we know that equilibrium, all those quantities are exactly the same for this whole system. Your question points us in the direction, okay, so what happens to the derivatives of those guys? Okay? We only used that the derivative of our energy is at 0. We haven't used that the energy should have a minimum. Right? So this is where we're going right now. Okay. So for this, we need to use some additional information about the properties of energy and entropy. Okay, so let's assume that we had two systems. S of U and V and N. This is energy. And exactly the same system on the right-hand side. So all the systems are identical. Those two systems are identical. S, E, V, and N. Now, I'm modifying a little bit my system such that, let's assume that I did it on purpose, somehow I managed to move by random fluctuation or intentionally, but I managed to move some energy from this part, from the left-hand side, to the right-hand side. So I have S, E, minus delta E, V and N. And here I have S, E plus delta E, V and N. Okay. So I'm taking your point of view. The system was in equilibrium. I did something. I pushed it a little bit out of their equilibrium where it was located, and I'm looking on what's going to happen. Okay, so I pushed the system a little bit out of equilibrium, then I released it, and what do I expect? I expect that if I'm going to leave the system alone, it's going to reach equilibrium, which is the point where I started. Okay, so the idea is I pushed my particle a little bit to the right, to the left. Since the system or the equilibrium is a minimal point of the total entropy or energy, okay, it will eventually go back to its original position. Okay, so if I'm looking on the system after a while, it will go back or have to go back to this specific characterization. Yes.
The volume is not changing between.
Let's assume that the volumes are not changing. Okay? But I can do the same trick with volumes and the number of particles and whatever. Okay, so to keep you in the loop, beforehand I haven't done anything and I was looking what happens exactly at equilibrium. Now I'm saying I was in equilibrium, I did something to the system, and I expect the system to return to equilibrium. And I'm using this property that the system will return to equilibrium to find new stuff about intensive and extensive variables. Okay? All right. So let's look on this property mathematically. So mathematically, we have the following thing. So we have S, and we have E. Okay. Now, we know from the second law of thermodynamics that S is a growing function of E. Okay, so it can be something like this. Okay? It can be something like this. So let's assume that our function looks like this. Okay? Now, what it means, let's assume that here is E minus delta E. Here it's E. Here is E plus delta E. Okay. Now, for E to the minus delta E, I have a very specific entropy, which is S of E minus delta E. Okay. For E plus delta E, I have another entropy, which is S of E plus delta E. Okay. All right. And this guy over here is S of E. Okay. So this now, this entropy is the entropy of the left-hand side. This entropy is the entropy of the right-hand side. And I'm looking on this picture, I'm saying there is something really wrong with this description. Okay. Why there is something really wrong with this description? Okay. Why I'm assuming that something really wrong? Because what happens if I'm plotting the line that connects those 2 points? Okay. If I'm plotting a line that connects those 2 points, what I'm getting is that for E, I will continue this line a little bit over here. I will get, okay, that the value or the height of this line, okay, is what? It is SE plus delta E plus SE minus delta E divided by 2. Do you agree with me? Right? So I'm saying the following thing, that S, according to this plot, that SE plus delta E plus SE minus delta E divided by 2 is larger than S of E.
Why we assume that it's larger?
Because for this plot, do you only for this plot, only for this plot, okay? And I'm claiming that this is really wrong. Why it's really wrong? Okay, so let's make another step. So SE plus delta E plus SE minus delta E is larger than 2SE. What is this 2SE? This is entropy at equilibrium. Right? So this is the entropy of the left-hand side and the entropy on the right-hand side. The total entropy is just the addition of the entropy of the left-hand side to the entropy of the right-hand side. Entropy is extensive. Great. So this is the entropy is at equilibrium. This guy is the entropy out of equilibrium. And we're saying the following thing. We do something to the system have to go back. Why? Because the entropy at equilibrium, it's at its maximal value. So if we push the system a little bit out, we get a lower entropy. The entropy have to go to a maximal value. This is why the system will go backwards. We assume that our entropy as a function of E looks like this. Okay? And what we obtain that it's actually the other way around. Where was the wrong assumption? No. My plot is wrong. Okay? This plot is erroneous. Why it's erroneous? Or what is the property of this plot that led me to the wrong conclusion? Maximum, so maximum value of entropy, it's a given, it's an axiom.
That's the maximum of entropy is the low.
The curve. The problem is that when I plot the straight line, okay, it was above the plot and not below the plot. Okay, so mathematically speaking, what is the name of this function? Convex function. In Hebrew, it's called kmura. Right? So you know what's kmura and kiura, or convex and concave? You don't know? I will explain it to you. Okay. So if I have, this is fx, and my function, it's like this is x. So I have something that looks like a cave, right? It looks a little bit like a cave. So this is concave function. In Hebrew, you say, well, it looks like, it's actually the other way around. Okay? So the name of this function in Hebrew, it's funkcja keura. Okay? So how I remember this, when you think about a ball, keara in Hebrew, okay? So it's always the other way around from what you think, right? So it's like, it's not a ball, it's you take a ball and you put it upside down. So this is funkcja keura. And you have a convex function, which looks like this. Okay. Funkcja kmura. So I always remember the naming because I always getting it wrong. I'm looking at this and I say, oh, it looks like a ball, so it should be kiura, but I know that it's always the opposite from what I'm thinking. So this is kmura and this is kiura. Now, any time that the function, the entropy, as a function of energy, will have convex properties, okay? What we are going to have, we are going to make again false assumptions. Why? Because around this, or in this vicinity of those convex properties, I can do this trick again and say, well, I'm getting out of equilibrium, and out of equilibrium my entropy is maximal. Okay? So this means that entropy for any energy, for any region of the energies, have to be concave function. Okay? So what we now understand, due to this small exercise, is that entropy is a concave function of energy. Entropy, concave function of energy. No, it's not related to the temperature. It's related to the maximal property. It's fine. So here, ds to dE is larger than 0, and dE to ds is also larger than 0. Right? Okay? So it's not the property of the first derivative, it's the property of the second derivative. Okay? So convexity or concavity, it's something that, it's a global property, okay? Because I'm not saying, oh, something happens at this specific point. Okay? Convex function tells us that for any x's, okay, if I pick x1 and I pick x2 and I draw a straight line between them, this straight line is going to be above the function no matter what x1 is and no matter what x2 is. Okay? This is what convex function means. It's not a local property, it's a global property. Concave function means the opposite. That if I'll pick x1 and x2, no matter what x1 and x2 are, okay, I draw a line between those 2 points. This line is going to be below the function. So what we have shown that entropy, it's not enough just to say that entropy is a growing function of the energy. It also has to be concave. This is wrong, and this is good. Now, yes?
למה אבל אמרנו שזה צריך להיות רק בנקודת השיווי משקל, למה אנחנו מחליטים שזה צריך להיות קונקייב לאורך כל...
Okay, all right, so the question why we assumed equilibrium. Exactly because we assume equilibrium, we're saying the following thing. We assume equilibrium, this is why SE plus delta E plus S minus delta E. Okay, so equilibrium means that the entropy at the new state has to be smaller than the entropy at the equilibrium state. Right? So S of E plus delta E plus S of E minus delta E has to be smaller than 2 SE. Because we're starting in equilibrium and because the entropy is maximum in equilibrium, this has to be always satisfied. And this, if you draw this on this picture, you will see that the straight line has to be below the actual function. Okay? Yes?
The entropy can a linear
can be a linear function. Well, yes. In general, it's nothing wrong with a linear function. It's a growing, monotonically growing function, and well, you cannot play this trick, right? So what will happen in your linear function? So the slope has to be larger. Okay? You're going to get an basically not an identity equality. Okay, and due to this equality, this property of maximum of entropy is going to be satisfied. Okay. All right. So this has always to be the case. Now, basically, what it means, it's a global property. Locally, it means the following. So convexity, concavity, concave property of entropy leads to that d squared s to d e squared, it's always smaller than 0. It's not the other way around. Okay, so for any concave function, the second derivative is going to be negative. But not every function that have a negative second derivative is going to be concave. Yes?
Does that mean that the temperature is increasing function energy?
So the other way around, 1 over the temperature is going to be the increasing function of energy. And it's fine, because it's 1 over the temperature. Okay? So it's not the other way around. If it was the other way around, you were right, but it's not. Okay, so where we're getting with this property. So we managed to get a lot just from saying, look, there is it's a function that is growing as a function of energy. Yes, we got all those equivalences of general forces. Now we have something a little bit more stronger. We don't only have the first derivative, we also have the properties of the second derivative. Where it's getting us? So first of all, this is the property of S. Okay. So we don't like to work with S, we like to work with energy, temperature, and stuff like that. So we want to take this and write something very similar for energy. Okay. Now, you can do exactly the same trick. And what is your trick is going to be? So if you have an energy of S plus delta S plus an energy of S minus delta S is going to be greater than 2 multiplied by E of S. Right? Where are we getting this? The entropy is at its maximal value. The energy is at its minimal value. So if we again draw those two systems, we had E of S and we had E of S. We did something, we put the system a little bit, slightly out of the equilibrium. So now we had E of S plus delta S, and we have E of S minus delta S. Okay? So we know that the total energy here, it's E of S, this is equilibrium. Here the total energy is E of S plus delta S plus E S minus delta S. And because of and due to the fact that at equilibrium the energy is at its minimum, therefore the system would like to go back to its original equilibrium state, and the energy at equilibrium is always smaller than the energy that we put the system at the out of the equilibrium. So if entropy is concave, energy is convex function. Right? So if concave means that this derivative is smaller than 0, what convex property means? That the second derivative of the energy with respect to entropy is going to be positive. D convex E means d squared E to ds squared greater or equal to 0. Okay. This is already something. Why it's already something? So there is a bunch of plots of two systems. I'm pushing the system a little bit out of equilibrium, I'm bringing it back, etc., etc., etc. But those are already concrete statements. This statement and that statement, and brings me back to your question about temperature, right? Because when I'm looking on this guy, I can say, oh, but dE to ds is temperature, right? Temperature is equal in all the different parts of my system. Fine, but how it's going to change as a function of something? So all of this story tells us that dt to ds is greater than 0. Now, this is a connection between conjugated variables. Remember that E is a function of S, V, and N, for example, and S is conjugated with D, V is conjugated with minus P, N is conjugated with mu. And we know how T and S are related. So we can ask the following question. If it happens for one conjugated pair, what will happen to the others? Right? Can we use the same formalism of saying, oh, we have two systems, we put them a little bit out of equilibrium, we learn something about this function is concave, this function is convex, blah, 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 blah. We have something about the derivative, the second derivative, and the second derivative of the energy, it's always a first derivative of intensive variable, of generalized forces, right? Because all the derivatives of the energy are intensive variables. It's going to be temperature, it's going to be minus pressure, it's going to be chemical potential, it's going to be tension, and then the concavity or convexity is going to tell us, well, you take the derivative with respect to something, you're getting it's either greater than 0 or smaller than 0. So those are stability relation. At equilibrium, we know that all the different variables are exactly the same across the whole system. But we don't know how they're going to change if we will try to put the system a little bit out of the equilibrium. Okay? So what we now are getting to is how they are going to be modified. If we take the system a little bit to the left, a little bit to the right, we have a connection between the behavior of the conjugated pairs. So let's do this for some other variable. Right? So what else we can do? What else we can do? Any questions? Yes.
Yes. According to what you said, the equilibrium that if we have a state that is not in equilibrium, dt to the s is greater than 0, but equilibrium you have to be at maximum temperature because you can't.
No. It's not saying that. It's not saying that. No. If I'm modifying the entropy and I'm bringing you from one equilibrium state to another equilibrium state, the temperature is going to rise. So if you have two equilibrium states and you increase your entropy a little bit, the temperature is going to rise. That's what it says. Right? Out of equilibrium, I don't know what's going on. Eventually, all of those descriptions are what happens in different equilibrium states. Okay? Good point. Now, I'm looking on this description and I'm asking, well, why couldn't I do this whole idea, okay, not with S, but with volume, right? So let's do the same thing with volume. We have a system. The energy is a function of volume. It's also the function of entropy. It's also the function of number of particles. But we concentrate only on the volume. Okay? Okay. We modify the system a little bit such that I have a little bit less or a little bit more volume on the left-hand side and a little bit less volume on the right-hand side. I know that the total energy here is 2E of V. And I know that the total energy over here is EV plus delta V plus EV minus delta V. Now, here, if you remember, at the first lecture I told you something. Energy is extensive, and it's very important that it's extensive. And it only works for macroscopical systems. So here, when I'm saying that it's extensive, I'm neglecting something. The interactions between those two. If the system is very small, or the interactions inside the different particles are very, 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 very prolonged, okay, this assumption won't work, and all our claims are not justified. Okay? So we only describe systems that are large enough such that the interaction energy between the different parts of the system can be neglected. Extensivity is crucial. So over here, the same as over there. the energy has to be at its minimal value at equilibrium. So we can say that E of V plus delta V plus E of V minus delta V is greater than 2E of V. That means that energy is a convex function of volume.
Stas,
Yes?
why do the volumes have to be equal in equilibrium?
The volumes don't have to be equal, it's just I'm using this example. They don't have to be equal.
Okay.
They don't have to be. It's just simpler to show it, the convexity in this way. That's it. Now, what it means, okay, so we repeat this for this system. So convex E means that the second derivative of VE with respect to V is greater than 0. Okay? So we have convex E means, okay, that locally d squared E to d V squared greater or equal to 0. Okay, so dE to dV equals to what?
Minus P.
Minus P. D minus P to dV greater or equal to 0. Okay? Another relation between our conjugate,
Stas, didn't you want E to be concave?
convex.
Convex.
Concave was entropy. You're forgetting what is concave convex. It's the opposite of what you're
Wait,
thinking.
so why is it opposite?
It's like me. I always think the other way. So whatever you think is the opposite.
Why is it opposite from entropy?
Because it was at its maximal. Right? Entropy, it's its maximal. Energy, that's minimal.
Oh,
That's
okay.
that's why it's the one is convex, the other was concave.
Okay.
Okay? Another relation between V and P. Okay? Now, if I do this again for number of particles, what will I get? D squared E to D n squared has to be greater than 0. I will just repeat this argument and I will push inside of volume or entropy. I will push the number of particles over here and I will get saying, oh, this is a system in equilibrium. This is a system, it's out of equilibrium. It won't come back to come back to this equilibrium state. This is why it's going to be convex function of the number of particles. This is why its second derivative with respect to n has to be greater than 0. And this means that d, what is dn to d? dE to dn is mu. So we have d mu to dn greater than 0. I can repeat this process again and again and again and again. Okay? And in general, what I'm going to get is that if you have an intensive variable and you take the derivative of this intensive variable with respect to its conjugated extensive variable, okay, this derivative has to be greater than 0. Right? Yes, let's write it down. E is a function of S, V, N, and Y. For any extensive variable Y, d squared E to d y squared is going to be greater than 0. X equals to d e to dy, x conjugated that variable to y. And it is intensive. And from here, we're going to get that dx to dy is going to be greater than 0. So you take any intensive variable, you take the derivative of this intensive variable with respect to its conjugated extensive variable, and this derivative has to be positive or equals to 0. So now we have a tool, okay, a general tool, to define equilibrium, to define what happens if we put our system a little bit out of equilibrium. And we're going to use this tool. Now, the majority of stuff that we have developed in thermodynamics in second year, maybe Bina haven't told you that, but it's all based on those two assumptions, or two results. That there are different intensive variables that describe the system, and in equilibrium, all those variables have to be equal to each other. Okay? Or the intensive variables of different systems in equilibrium have to be equal to each other, and that the properties or how they're going to be modified if with respect to each other satisfies this equation over here. Okay? Bina haven't told you all of this in those terms, but all the Carnot engines and all the other stuff, expansion of gases, etc., 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 etc. It's basically based on those two general results. I'm not going to repeat whatever you have already learned in thermodynamics, even although the language probably is a little bit different from what you used to. I'm going to push us a little bit forward towards the field of phase transitions and how all of this is related to phase transitions. Okay? So basically, what I've taught you today is called stability criteria. So let's write it down, at least for the usual variables, stability criteria. What is stability criteria? Is that if we have two systems, first of all, and we have TA, and we have PA, and we have what else? NA, as here it's TB and PB and NB, and those systems are in equilibrium.
Why are you choosing two extensive variables and one extensive?
No. So because here it's the equality of the intensive parameters of two systems. So this is part A.
Okay, so why don't you use mu?
Mu. Here. Yeah. It's my mistake. You are completely right. Mu A equals to mu B. Okay? But it's not enough. We also know that dt to ds is what? Is greater than 0. We know that d minus p to dv is greater than 0. And we know that d mu with respect to d n greater than 0. Any system at equilibrium have to satisfy those criteria. If they are not satisfied, the system is out of equilibrium. Now, what I want to show you, maybe later. So what I want to show you that how we are going to apply applications of stability criteria to phase transitions. Okay, so I won't define exactly now what is a phase transition. I will do it next week. But I want to show you a simple example where those criteria hold and when those criteria break. And we start with something that you already seen at thermodynamics, and this is the state equation of ideal gas. Okay. Ideal gas. So what is the equation of ideal gas? PV equals to nRT. So R is a constant, gas constant, N is the number of molecules inside, T is the temperature, P is the pressure, V is the volume. Now, how P looks as a function of V. Why I'm looking on P as a function of V?
Because this is the intensive and extensive.
Exactly. They are two conjugated, it's a conjugated pair, extensive variable, V extensive, P conjugated intensive. They are related somehow, and not just somehow, by this specific relation. Okay? So we know that d minus p with respect to dv is greater than 0, meaning that dp to dv is smaller than 0. Okay. So if we plot p as a function of v for different temperatures, how this looks, so P equals to nRT divided by V. Okay. So for different temperatures, we always have a decreasing function. So I'm plotting isotherm. Isotherm, I'm setting the temperature constant, and I'm looking on the behavior of the pressure as a function of the volume. Okay. So for different P's, the plot will always look the same. It's a decreasing function. Boring, decreasing function. And for any temperature, the stability criteria is satisfied. For any T greater than 0, the stability criteria is satisfied. What it means that, what is ideal gas? Right? I put a lot of particles in a chamber. Okay? So those particles have only kinetic energy. Right? They do not interact with each other. They do interact with the walls. This is why I have pressure, because from time to time they bombard the walls, and those bombardments are somehow trying to push the walls outside. This is why I have to keep a pressure to put the walls at the same position. This is why I have pressure. But the idea of ideal gas, that all those different molecules never see each other. They do not interact. So you can basically say that ideal gas, it's a very dilute gas, where the probability of encounter of two molecules is extremely small. Okay? This system, if put in a box, and if I keep the temperature constant, satisfies all my conditions about equilibrium. Okay, and it can be in equilibrium. It's very, very nice system, but it's exceedingly boring. Very, very boring system. Great. We can solve it exactly. We can write whatever you want about the system, but it's a boring system. Now, in the 19th century, a guy named van der Waals said, well, most of the gases do not behave like this. And this simple equation of the ideal gas, well, it's a good approximation, as I told you, when the gas is very, very dilute. Okay? It's a good approximation when the gas is dilute. But what happens in reality is that those particles, if I'm putting here more and more and more molecules inside, those particles start to fill each other, right? Moreover, there are no point particles. There are balls that have some, well, not exactly ball, but you can assume that they are not point particles. They have intrinsic volume. Okay, so the assumptions of van der Waals gas is that we have to modify stuff a little bit. Okay, so the modifications that were introduced by van der Waals are the following. So first of all, V. So volume, the total volume of the system, okay, the volume that enters this equation, it's the free volume of the system. Okay, so if you look on how exactly this equation was derived, so it's the volume of this chamber. But some of the volume of the chamber is occupied by self-volume, we can call it, of those particles. Okay? They take some of the volume, right? So it's not that so the volume that we're looking, the total, the free volume, that's what's important. It's not this. So volume have to be modified by taking out of this system the self-volume of the total of the particles. So the N is the number of particles. Let's assume B as the self-volume of each of the particles. So volume is going to be decreased a little bit by the total number of particles in the system multiplied by the self-volume of each particle. Also, the pressure, well, the pressure is not just the pressure of the walls, right? The pressure also has to be modified somehow. So the suggestion of van der Waals was, look, the pressure also depends on the concentration of the molecules inside. Because if the concentration is really, really, really low, the pressure is the pressure that the particles are just pushing each other on the walls, because they do not encounter with each other. But if the density of the particles inside the chamber is high, the pressure is not just the pressure of the bombardments, it's also the pressure that's related to the density of the particles inside the box. Okay? So he said the pressure have to be modified by the pressure that we measured plus some constant A and divided by V. This is big N, this is big V squared.
This is the new V or the V that's...
This is the free volume. Okay, so eventually, let me write down the equation as van der Waals wrote it. He said the following. Instead of just taking this P over here, we take a modified pressure. So P plus A and divided by V squared. Instead of taking the volume over here, we are taking modified volume, which is V minus ND. What you are referring to are second order correction terms. Van der Waals give them out. And this equals to nRT. So this is called van der Waals equation. Great. So you say, well, PV nRT, P plus something more complicated, V minus something equals to nRT. Who cares? First of all, experimentally, for higher concentrations, not just very diluted gases, this works extremely well. Way, way, way better than you expect from the ideal gas. Okay, so this is actually, from experimental point of view, even if whatever van der Waals have done is just to feed the data, works extremely well. But there is more merit to this equation. Okay, so here we plot different isotherms of P as a function of V. Let's do the same. Let's do the same for this equation. I won't tell you exactly. It's solvable. It's not really hard to solve, right? It's solvable. And when you solve it and plot P as a function of V for different temperatures, you start to see something which is quite nice. So this is P, this is V. And you start from high enough temperature, from high enough temperature. So if you take this guy out of here, so it's P plus A N divided by V squared equals to nRT divided by V minus NB, or P equals to ANV squared minus plus nRT V minus NB. Now this basically says that the volume cannot be larger than something else or smaller. So if you plot this guy, so if you plot this behavior, and if your temperature is high enough, you just see this same behavior. So if this is high temperature, high T, high temperature, it behaves as an ideal gas. The particles, basically, this is just a decreasing function. The particles don't see each other. When you lower the temperature, start to see something peculiar, right? And when you lower the temperature even more, at some point, start to see this behavior. So the function starts to develop a minimum and a maximum. Okay? Well, you can say, well, very nice. Nice functions. During my high school, I explored the properties of the minimum and the maximum, and I can find it for any function, right? But this is a problem. Why it's a problem?
Because the derivative is...
Exactly. So we have a region over here, and what happens at this region is that the derivative of P with respect to V is greater than 0. And this is bad. Why it's bad? Well, maybe it's bad for van der Waals, right? So what van der Waals tells us? Van der Waals tells us I have a great equation that describes all those different gases extremely well, but it doesn't work for the basic assumptions of thermodynamics. Right? Now, moreover, so if you're thinking, well, dP, dV greater than 0, why it's bad? It's also bad if you reverse this. If you reverse this plot, and you plot V as a function of P, you will see that it behaves something like this. So what happens is that I have some specific P's over here. Okay? I have some specific P's over here that there are different values of different volumes. Okay? This is why it's bad. It's not only that, well, the derivative is greater than 0. The implication is that there are, for one specific pressure, there are different possible volumes of the system. Now, equilibrium defined by one specific set of pressures, volumes, etc., 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 etc. It can be true. Something is really, really, really wrong in this region. You can say, well, something is really, really wrong with the van der Waals equation, right? So, well, who cares about those theoreticians? They write equation, Stas haven't explained properly to us what exactly this term is and why it's... No, so he was wrong, that's all, he was wrong. But no, he was right. But this region this region, there is another explanation. Okay? So we assume that the system can always be in equilibrium. And there are smooth transitions from one equilibrium state to the other equilibrium state. Okay? But sometimes the transitions of the system from one equilibrium state to another equilibrium state are not smooth. They are violent, they are disruptive, they are big, they are not small. Sometimes we modify our parameters a little bit and the system just explodes. It modifies its behavior by enormous amount. This is called a phase transition. So what comes out of this description of van der Waals, that even in gases, by looking on this property, this stability property, you can find phase transitions. So the system won't go smoothly from this point to this point to this point to this point. What will happen, and we'll see it later, actually, that the system will reach some specific point over here, and if you increase your volume a little bit more, or you decrease your pressure a little bit more, you will suddenly jump from here to there. Right? So there are no smooth transitions that going like this. The transition will be you reach over here, and there is an abrupt transition to some other place. And this abrupt and large jumps of the system, this is what we call phase transition. And I will show you examples of phase transitions next week. Thank you. בוודאי.
זה פייס טרנזישן של כאילו...
אני לא הגדרתי לך מה זה פייס טרנזישן.
כן.
לא סיפרתי לך ולא הראיתי לך, אבל אני אקרא לזה פייס טרנזישן.
אבל הדילוג על הדבר הזה...
יש מעבר פאזה מסדר ראשון, יש מעבר פאזה מסדר שני. ברגע שיש לך קפיצה גדולה, אפילו שהשינוי שלך הוא אינפיניטסימלי, זה יהיה מעבר פאזה מסדר